Okay, so we're looking at problem number 2 of the ionization energy lab. And I'm not sure what I even titled that. What did I title that? Electron configurations and ionization energy.
Mm-hmm.
Yeah, this used to be titled shells, subshells, and orbitals. Oh my. But the idea here is that we can look at ionization energies to see, as it were, shells, subshells, and orbitals. And so it has to do with this formula here that I'm going to show you in just a moment as soon as I change my share. So boom, boom, zoom, share. And we're looking at the lab itself. So here you can see that the force of attraction is equal to K n minus E n plus E over D squared. That's all multiplied together. K is some constant. E is a constant. It's the charge on an electron. N plus is the charge of the cation, and N minus is the charge on the anion. So it could be like a -1, -2, -3 for the anion. It could be a +1, +2, +3 for the cation. And D is the distance between the charges. So how does this apply to ionization energy? Well, with ionization energy, we're essentially removing an electron from an atom completely. So the distance between them is infinite, if you will. Now, we don't want to use that to judge the force of attraction, because if we use infinity, the force of attraction is 0. But nonetheless, D doesn't really matter for the force of attraction when we're trying to calculate the energy it takes to take an electron. So take a look at the two ionization energies for helium. Do you see that we have the first ionization energy results in a +1, and the second results in a +2?
Okay.
Okay, so when we apply the force of attraction here, you see that little thing that says, looks like a, I don't know, a half of an infinity sign?
Mm-hmm.
That means proportional to. So the force of attraction is proportional to the positive charge. It's also proportional to the negative charge. It's also proportional to the distance between them. But in both cases, the distance between the ions being separated is the same, so that falls out. The negative charge in both cases is -1, so that falls out. So that means that the force of attraction will depend only on the charge of the positive ion form. In one case, the first one, it's a +1. In the second case, it's a +2. So the idea here is that when you take that second electron from helium, it should take about twice as much energy as the first one. Because if the electrons are equivalent, they're the same. Okay?
Mm-hmm.
So our first one takes 2372, and if you double that, you get 4742. So you could say, roughly speaking, the second electron taken 5250 is roughly twice that of the first. It's a little bit more, though. Okay? So if we go to the question here, does the pattern roughly fit what is expected if the two electrons are equivalent? Well, I'd say it roughly does. We could even calculate a percent error. The percent error would be 4742 minus 5250 over 5250 times 100%. And roughly speaking, that's about 9% error. So in chemistry, if you're within 9% of what you expected, you're doing a little dance. You're like, oh, wow, look, we're on to something. If it was 100% off, you'd be like, well, darn, I don't know what we were thinking. Clearly, we're wrong. Okay, so I would say that roughly, yes. Now, furthermore, what do you expect the electron configuration of helium to be?
1s2.
1s2. So doesn't that mean that both electrons are in the first shell?
Yes.
And they're both in an s subshell?
Yes.
And since there is only one orbital there, they're both in the same orbital.
Mm-hmm.
So I would say, yeah, it does justify the idea that they seem to be equivalent.
Okay.
Now, here's something that is kind of interesting is why is it not precisely double? Can you imagine why? And this was not
Because
a question that was asked.
is it because the distance is less because it pulls closer to the nucleus after you take that first electron away?
No, because the
Hmm.
nucleus is the same size.
Okay.
If
I don't know.
anything, you would argue this. Do you know about shielding or screening versus penetration?
I know about the shielding being from the inner shell electrons, which I wouldn't think would matter because there's only one orbital.
Well, in this case, there's one orbital, but there's two electrons, right? And
Oh, is it the repulsion?
it's the
Because,
repulsion, and you could
okay.
consider it to be screening or shielding because there's nothing to say that both electrons are the same distance from the nucleus. They're just somewhere in that
Mm-hmm.
sphere. And so technically, unless they're both precisely the same distance from the nucleus and maybe on opposite sides, there is the opportunity for one to screen or shield a nucleus from the other,
Okay.
making
makes
it
sense.
easier to take the first one.
Okay. Yeah.
And with the second one, since you don't have any screening, it's going to be harder to take. So another way to kind of wrap that up or summarize that is you could say, well, the electrons are repelling one another.
Mm-hmm.
So the first one to take is being repelled by the other one, but the second one is not being repelled by anything. So you got to put in the full measure to take it out.
Okay. That makes a lot more sense for the periodic trends for like the D block, where you just get so many electrons crammed into a space. They
Yeah.
really are just shielding each other as they're moving kind of in a circle. Because I always thought of it as like just a
Yeah.
band as opposed to just a big floating space.
Yeah, this is not like the lines at the supermarket where you're spaced 6 feet.
Mm-hmm.
You could be anywhere in that 6 feet.
Yep. Okay.
That's the deal there. So that's number 2.
And number 3, my main question was, it says on the y-axis to have energy. What does that mean? Does it mean like effective nuclear charge or?
No, so that would be on the y-axis. You're gonna top out at like 5,500 or 6,000.
Okay.
So I'm going to do a different share with you.
Well, the ionization energy is on the x-axis. So what would the y-axis be?
Actually, graph the energy on the y-axis and the IE on the x-axis. Use 1 for IE1 and use 2 for IE2. So let me show you what I'm looking for, okay?
Okay, yeah.
So this is going to be the ionization and the ionization number. So there's 1 and there's 2.
Oh, okay.
The first one was what, 2372,
Uh-huh.
and the second one was 5250.
Uh-huh.
So this should be about
Okay.
not twice as much, but a little bit more. So it's going to look like this and this.
Okay. So the number on the bottom and ionization energy on the Y. Okay.
When
Perfect.
you graph this, you're going to find that it comes pretty close to the origin.
Mm-hmm.
And whenever you see this type of relationship where it goes back to the origin, you would say there's something about these two electrons that you're taking away. This is weird. This is the first one taken away, and this is the second one.
Mm-hmm.
When they grab back to the origin, you say, well, they're similar to one another.
Mm-hmm.
Okay, and then the next thing here, I'm going to do a share back to the lab. If we look at number 4, we're supposed to look up the ones for calcium, find the ionization energies, and graph them as we did for helium. Now there's 20 of these suckers.
Mm-hmm.
Now, roughly speaking, the graph is going to look as follows. So it's a 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2 for calcium.
Can you switch your share?
Yeah. Well, I'm not drawing anything yet.
Oh, okay.
I'm just writing out the electron configuration,
Gotcha.
which is right here, to help me show you what's probably going to happen with this guy.
Okay.
The 4s2, these are going to be the easiest to take.
Mm-hmm.
So you're probably going to get, for 1 and 2, you're going to get dots that look like this. They're really close to 0. And this top number here is probably going to be like 20,000 or some huge number.
Mm-hmm.
So these two are really easy to take. Then the next 6, 4 or 3, 4, 5, 6, 7, 8. So these are the 4s2. These are going to be the 3p6. And because they're from the 3rd shell, not the 4th shell, they're going to be much harder to take. So you're going to see all of a sudden an increase where it looks kind of like this. And then you're going to have the 3s2 next. So here's 9 and here's 10. And since they're the 3s, they're still going to be close to the p's, but a little different. And then 11, 12 are going to be the 2p6s. So here they're going to rise again. 1, 2, 13, 14, 15, 16, 17, 18, 19, 20. So these are going to be higher yet. And then there's supposed to be 6 of those, and then 2 more of these. And then the last 2 are going to be like this, way up here. And these are the 1s2. They're the hardest to take because they're closest to the nucleus. But the idea here is that when you graph these, you should notice that roughly speaking, these all go pretty close to the origin. And what does it mean when they all graph back to the origin? It means these two are similar. So the 1s2 are similar, the 2s2 are similar, the 2p6 are similar, and so forth and so on. I don't think I asked you to graph all 20 of them together, but I'm going to do something else here in just a minute. I'm going to go back to the, I'm not going to do the share. I'm just going to go back and see what I wrote here. So notice the 20. They do not form a, oh, I did ask you to graph them.
Mm-hmm.
So for the 20 points, they do not form a straight line back to the origin. Have you graphed those yet?
No, I haven't.
Okay. Have you looked up the numbers yet?
Yes.
Okay. So if you look at the first 2 numbers, what are they?
589 and 1145.
Okay. So 589 and 1145. Do you see how that the 1145 is roughly double what the 589 is?
Uh-huh.
Now what's number 3?
4912.
Do you see how all of a sudden 4912 is not 3 times what 589 is?
Mm-hmm.
This is what you'd expect if they were similar. It's jumped up to a whole nother level.
Mm-hmm.
Now what's number 4?
6490.
6490. So here, I'm going to try and do a fairly accurate job here of graphing that. And I do have some graph paper here. I just need to get my hands on it. Okay. So here's my graph paper. And I'm just going to draw this like this, not trying to pay any special attention here. Can you see what I'm drawing here?
Uh-huh.
Okay, so I want to go to 6490. Why don't you give me the other ones for 5, 6, 7, 8, 9?
81, 8140,
Okay,
10,500,
okay,
12,270,
okay,
14,210,
okay.
18,190,
What's number 10?
20,380,
Okay, and then go ahead and give me just 11.
57,080.
Okay, so without even graphing, can you see that there is a distinct break between 10 and 11?
Uh-huh.
And there's a distinct break between 2 and 3?
Uh-huh.
So what does that mean about 3 through 10?
3 through 10 are in the same subshell?
No, I would say they're in the same shell.
Oh, shell. Yep, you're right.
And so here, I'm going to attempt to graph 1 through 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to go up to 20,000. So here's 1,000, 2,000, 3, 4, 5, 6, 7, 8, 9. Actually, each one of these is going to have to be 2,000. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is 20,000. So if we do number one is about right here, right?
Mm-hmm.
And number 2 is about right here. And number 3 is all of a sudden right here at about 5,000. 4 is at 6490. 6490 is about right here. And then 8100 right here. And then 10.5, 10.5 about right here. And if you take a look, do you see how these two go back to the origin?
Uh-huh.
Do you see how these 3 go back to the origin?
Mm-hmm.
And then does it look like this next one is in line with the first 3?
Not quite.
Not quite, right?
Yeah.
Because if you look at the jump from here to here, it's about 1,500, right? And the jump from here to here is about 2,500.
Uh-huh.
So there's something going on there.
So that's the first solo electron you take out of an orbital?
You are dead on.
Okay.
These are all paired.
Mm-hmm.
The first paired one, the second paired one, the third paired one, and then boom, you no longer have that electron helping to push the first one out.
Okay.
So we would expect number 7 to be kind of in line with this one. And if you look at the difference between 6 and 7, it's not 2,500, but it is, closer to 2,000. So let's see where that is. 7 is 12,270. So this is 13. So 12,270 is about right there. 8 is 1410. And so we're now at 2,000 again. 14.2 is right here. And roughly speaking, without pulling out my straight edge, okay, with pulling out my straight edge, you can see that even with my rough graph, it shows that those pretty much go back to the origin also.
Mm-hmm.
So if we were to look at these, 1s2, you probably can't see this, but hopefully now you can. 1s2, 2s2, 2p6, 3s2, 3p6, 1, 2, 3, 4, 5, 6, and then 4s, whoops, I did that wrong. 4s2 right here. This would be our first one. This would be the second, third, fourth, fifth, sixth, seventh, eighth. And we can see that the ionization energies show us that there is something similar about the first one of each of these and something similar about the second one of each of these. And since they're roughly the same slope, there's something similar about all 6 of them. Now, these guys are at 18,190
Mm-hmm.
and 2381. So that's here. You can see that these two are also similar, but this big old jump says, you know what? While these slopes are very near to one another, and this one down here is very different, all 10 of these electrons are similar, but there's a set of 3, 3, and 2.
Gotcha.
So clearly, if I want to graph all 20 of these, I wouldn't top out at 20. What was your biggest number for number 20?
527,000.
So you're going to top out at 500,000.
Mm-hmm.
All of this is going to kind of flatten out. But it does serve a purpose to just graph the first 10 alone.
Mm-hmm.
And you can actually see shells. These first 2 are in the first shell, the 4s. These next 10 are in the second shell. When I say first shell, I mean the shell that's easiest to remove things from.
Mm-hmm.
So that's the 4s. These next 10 are in the shell that's next easiest to remove them from, which is the third shell. And these first 3 are from the 3p that are paired. These second 3 are from the 3p that are unpaired. And these last 2 are from the 3s.
Can you scoot the paper down a little bit so I can see the 4s ones?
Yeah. Well, these are the 3s. These are the 4s.
Oh, 3s, yeah.
So these are the 4s.
Mm-hmm.
These are the 3p paired. These are the 3p unpaired. And these are the 3s, I'm sorry.
Mm-hmm.
So the kind of how do I say this, confusing thing about all of this is that we're looking at it backwards. Instead of 1s2, 2s2, we're looking at 4s2. We're looking at it from the other angle.
Yeah. But it still serves a good purpose because it really explains a lot of periodic trends and things like that. It's pretty much the entire chapter in one paper.
Yeah, and actually what this does is it gets us to understand that the ideas that there are shells, subshells, and orbitals
Mm-hmm.
is that there's experimental evidence for it, not just a guy named Schrodinger came up with this idea and said, okay, this is the way it's going to be.
Mm-hmm.
And then Hun came along and said, here's how we put electrons in. And Pauli came along and said, okay, no 2 electrons can have the same set of quantum numbers. All of this was built out of experimental data that they knew about. And then trying to explain it. And they go hand in hand.
Yep. Cool.
So number 4 is graphing all of that. And here I asked some questions like, based on just what I graphed here, which are closer to the nucleus and which are farther away?
Furthest away are the first set, the 4s.
And why are they the farthest away?
They're the easiest to take.
They're the
They have
easiest.
less pull.
Yeah.
Mhm.
And what does each set of quantum electrons represent? So when you graph this, I'm going to draw a really crude thing here. So this is 100,000. This is 200,000, 300,000, 400,000, and 500,000. So the first 2 are going to be like this when you look at them. And the next 10 being at under 20,000, they're going to be like this. What is number 11 was 57. What was number 19?
494,859.
Okay. And what was 18?
111,704.
Okay. So our next 8 are going to go from 57 to 111. So this is roughly 57, and this is roughly 111. So the next 8 are going to be like that. and the last two are way up here. So, the question here is, well, what's that? What's that? What's that? And what's that? Well, this is the easiest shell to take them from. That's the fourth shell. This is the third, this is the second, and this is the first. So this is kind of, if you will, evidence that there are real shells, and the electrons are not all just hanging out around the nucleus with the same amount of energy. So there's that. So the second part of number 4 says, what does each set of electrons? This is a set, this is a set, this is a set, and this is a set. Each set is a shell of electrons. And number 5, now that you are armed with this, what do you expect for neon? So neon is supposed to be a lot easier than looking at calcium. How many electrons do you have with neon?
10.
Okay. And we already know what the electron configuration is. It's 1s2, 2s2, and 2p6, right? So roughly speaking, we expect the 2s2 and the 2p6, the first ones to be taken, right? And so we expect that. And then what do we expect for the 1s2? Something like that. So 2 shells.
Yep.
And this is a really rough graph. You're not supposed to have numbers on here, except for this would be 1, 2, all the way up to 8, and then 9 and 10. And then when you look them up and you graph them, you're going to find out, oh, it does look roughly like this.
Okay.
Now, for this one, you might also be able to see the detail where this, and this are a little bit different than these 3, which are a little bit different than those 2. I'm not sure if you can see it for neon as well as calcium, but you might be able to see that.
Okay.
Okay, and then let's see, number 7. So here, are the energies closer together for large shell or for smaller shell? So take a look at these energies. Are they closer together here where I'm running my finger, or here where I'm running my finger?
I think they're closer together for the large shells.
Okay, so they're closer together here, right? What I mean by that is if you look at the distance here compared to the distance here, energies are closer together here. And here, we know this is the second shell and this is the first. So like you say, they're closer together for the large shell. And actually, we're supposed to do this with the calcium. And the calcium looks like this. Boom, 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 and boom. So here they're closer together for large shell than for the smaller shell. 8. Oh, this is the hard one. So 8, I've already talked about, but I did it with calcium where we looked at that first 10. So hopefully you'll be able to see that for neon.
Yeah, I think so.
And then number 9, it says go back to helium. You know, it's not twice as much, actually more than twice. So I kind of gave away that one.
Yeah.
Why is it more than twice?
Because the shielding or lack of shielding.
Right. Or you could say it's because the first one is being repelled by the other one, so it's easier to take away. Whereas the second one, you're not getting that little help from the other electron. All righty.
Yay. Okay.
I'm guessing that you probably want to get at this rather than spend more time on it.
No, I'd rather go ahead and finish it. I've got tons of stuff to do today. So
I imagine you want to call it quits now, and we'll just, you can call again, and don't forget you can email me questions if you want.
Okay. Awesome. Thank you so much for your help.
You bet. Have a good day.
You too.
Bye-bye.
Bye.